I am Rashan Soy, and I will present you our work on misclassification risk and uncertainty quantification in deep classifiers. When we train deep neural networks, we usually assume that misclassification errors are equal. However, the cost of misclassification can be significantly different from case to case depending on the context. In this work, we discuss the importance of considering the risk and uncertainty quantification together. In standard neural networks, we usually use softmax function to predict a categorical distribution. However, this leads to overconfident wrong predictions. To address this, previously evidential deep learning is proposed, where the network predicts a Dirichlet distribution instead of directly a categorical distribution. A Dirichlet distribution is the prior of the categorical distribution, so we can easily use it to model the uncertainty of the categorical distribution. Here at the left, you see a Dirichlet distribution with all parameters 1. This indicates the uniform Dirichlet distribution and have the highest possible uncertainty. As we have higher counts, we have more evidence for different categories. For instance, here we have more evidence for the third category, which has counts 15 and more than others. So when you sample a categorical distribution from this Dirichlet distribution, it's more likely that you pick higher probabilities for the last category. The sum of these parameters indicates how certain we are. When we use evidential deep learning, we are able to estimate the uncertainty of our predictions. Here is an example. If you use a standard neural network with a digit 1, it gives the correct predictions for it with very high probability. But when you start to rotate counterclockwise, the network starts to think that now this image belongs to digit 2 or 5, which is wrong. And unfortunately, the network is quite confident providing high probabilities. On the other hand, when we predict a Dirichlet distribution, when we rotate the example, the network doesn't make a wrong decision. Instead, it increases the uncertainty by providing uniform Dirichlet distribution. In this work, we combine the standard evidential deep learning with picnic probabilities, which have been introduced in decision theory to represent the probability that a rational agent will choose a particular option when it is required to make a decision. So the neural network provides not only the evidence which will be used to calculate the Dirichlet distribution parameters, but also a picnic prior counts, which is used to weight the prior Dirichlet distribution based on the risk of making wrong decisions, misclassification decisions. In order to do that, we take the evidential deep learning standard loss, which is here, and combine it with the risk of making misclassification, which is represented by matrix R. Here we have the evidence output of the network and the picnic prior count. And we take all of these total loss to train our network. We evaluate our approach using 3 datasets, MNIST, Fashion MNIST, and CIFAR-10. Our experiments indicate that our approach has similar or even better accuracies for classification while reducing the cost of misclassification significantly. We also consider the ROC and precision recall curves to estimate how calibrated our uncertainties are. And this indicates that the predictive uncertainty of our approach is more informative for testing if a prediction is correct or wrong. Our approach allows us to train evidential classifiers with the risk of misclassification and reduce the risk of decision making when the uncertainty is high. As a future work, we will extend our approach to address robustness against an uncertainty quantification for adversarial examples. Thank you very much.